This is section 3.7. This will be the first video we do on the chain rule. So to give you a feel for the chain rule, I have a couple of examples here. So the first one, so H, that variable, represents the amount of homework that you've done. D is the number of donuts you've eaten. And T represents time. And so as we saw in chapter 3.6, we saw derivatives as a rate. So we're going to look at one rate. So the first is the amount of homework you've done compared to the number of donuts you've eaten. So here's how it works. The rate of homework done to donuts eaten would be 4 assignments per donut. So I could put units there. Assignments per donut. That's what that represents. And then the next one, we have another rate. How many donuts you've eaten with respect to time. So we have the rate of 3 donuts per minute. So if we combine these rates, we can find the rate of how much homework you do with respect to time. So if you think about this, how fast are you doing your homework? The rate of completing homework. Well, we know the rate of homework compared to how many donuts you eat. So we have DHDD. That's how fast you do your homework compared to how many donuts you eat. And we multiply that by dt, and that's how many donuts you eat with respect to time. So logically, if I eat or do 4 assignments per donut, and I can eat 3 donuts per minute, that's pretty fast. You guys are eating fast. If you look at this, it seems logical that these donuts cancel, right? And so, in essence, we do 12 donuts, or excuse me, assignments. I guess I'm hungry. 12 assignments per minute. Maybe I should have hours. That's pretty fast. That's way too fast. I should do time is hours. That would be more reasonable. So a smarter answer would be change this to hours. And so this unit here, I like that better, per hour. And we change this one to hour. That makes more sense, even though it still doesn't make sense. So you see what's going on. Hopefully, it's 4 assignments per donut, but you do 3 donuts per hour. So in essence, you do 12 assignments per hour. And those are probably small assignments because, yeah, that's not much. I mean, that's a lot to do in an hour anyways. But this is just for example purposes to give you an idea of how the chain rule works. I did another example, making snowballs. So H represents the number of snowballs you can make, or you've made, actual made. S is the amount of snow that's on the ground. And T is the amount of time. So you have a rate of 7 snowballs per cubic meter. So the rate of snowballs made with respect to the amount of snow. So the change in the amount of snowballs with respect to the amount of snow that's available. So that rate is 7 snowballs per cubic meter. And then you have another rate, the rate of snow falling with respect to time. So this is basically a change in the amount of snow over the change in time, which is 2 cubic meters per minute. So that's the rate of snow falling. And so you have 2 rates, and again, the change in the amount of snowballs made over the change in the amount of snow is 7 snowballs per minute, cubic meter, sorry. So we want to find how many snowballs you make in a given amount of time, or how many snowballs that are made, not necessarily you. And so we want dH dt, but we know dH ds, and we know ds dt. And so again, if you look, in essence, the dS's cancel, and you end up with dH dt. So let's do that. So the rate of the number of snowballs made with respect to time would be 7 snowballs per cubic meter of snow times 2 cubic meters of snow per minute. And you will see we get 14 snowballs per minute. And that will be our rate of which snowballs are made. So that's the idea of chain rule. What is the chain that's happening? And sometimes the chains are longer, but here are your chains. Those are your 2 chains. You're chaining 2 things to get what you want. And again, here are your chains. You're chaining 2 things together to get your rate. So that's what's happening here. Now the chain rule, this stuff I will get rid of. So here is the chain rule in terms of functions. And the hardest part for some of you is to see the inside function. But when you have a composition of functions, you're actually able to find the derivative. So we have a function g inside of the function f. So you need to practice recognizing which functions on the inside or you will struggle. So this is a composition of functions. So what we're going to do, we define the inside function. The one on the inside is u. So if that's u, this will be f of u. All right, so we want, and this will make sense when we start doing some examples. We want dy dx, the derivative of y with respect to the variable x. So from the previous examples, we know, okay, let's look at this previous one here. We wanted dH dt. So we needed a dH on top. And so we're able to find a function with dH on top. But we want dt on the bottom, so we need another function with a dt on the bottom, and that would have been this one here. And then with these canceling, you end up with what you want, dH dt. So that's the thought that you have. So if you want dy dx, you're going to need something dy. So if you look at this, I can find a dy du, because our variable is u. So that's what that is there. But we want an x on the bottom there, so we want a dx. So we need to find an equation with a variable x, and that's that. So that would be the change in u with respect to x, which we have here. So if you look, and those cancel, you end up with what you want, dy dx. So that's what's happening there. So looking at what we have, if you look at this, our function's y, our variable's u. So we're able to find a dy du out of that. And if you look at this one here, our function's u, our variable's x. What are we able to find? We're able to find a du dx out of that one. So if you look, there's our dy du, and there's our du dx to find dy dx. So you can kind of think about that, and I'm going to do a bunch of examples. 6 examples, and then we'll be done with this video for the intro to chain rule. So the first step, you need to recognize the inside function. So here we have a function inside of another function. Hopefully you can see that this 5x plus 4 is on the inside. So because of that, that's my u statement. That's my u, the inside function. U will be 5x plus 4. Now, if I do that, my original function becomes y equals u to the 6th. So hopefully you see what's happening. I've defined u as 5x plus 4. So this whole thing here becomes u. So it's u to the 6th. Let's keep going here. So I'm able to find the change in y with respect to u. And you have to realize u is our variable now, so it's going to be with respect to u. And that's going to be 6u to the 5th. So we use our power rule. The 6 comes in front, decreases 6 by 1. That's dy du. Then, if you look at this one, we can find du dx because our function's u and our variable's x. And just taking the derivative normally, we find that to be 5. And so our statement we're going to have, ultimately, we want the derivative of y with respect to x. So we're trying to find dy dx. Well, first, we need dy du, and multiply that by du dx. And so you see, that's going to give us our dy dx. So let's go ahead, and we found those values. What is dy du? It's 6u to the 5th. We found that. And then what is du dx? Well, that's 5. So now we get 30u to the 5th. But here's our problem. Our variable is supposed to be x. We have to replace u with what u is here. And we get 30, 5x plus 4 to the 5th. There is our answer for number 1. Now, let's look at this. What if we did not have the chain rule? This would get very ugly because you would have to do this. Let me erase that. I'm just going to show you how hard this would be without the chain rule. So one way is you multiply all this out, do all the distributing, and then you just use the polynomial, take the derivative of the polynomial. Or, even uglier, you could break this into 2 blobs and do the product rule between the first blob and the second blob. But when you take the derivative of that, you'd have to make another product rule, break it into 2, and just keep on going and going and going. It gets very ugly. You do not want to do that. So the chain rule is a lifesaver. It enables us to take derivatives of things that we couldn't before. So the next one, I'm going to show you what's going on. Number 2, our function's y, our variable's x. So ultimately, what we're trying to find is dy dx. But now I could rewrite this. Okay, first of all, this is going to be a problem for some of you until you see it. This, the way it's written, is actually this. It's actually sine x, the whole function cubed. So you could do a product rule with the old way, but you're going to find the chain rule so much easier. So this is sine of x cubed. Now I want to point out, let's look at number 3. This is very different. This is sine and then x cubed. So here's the big difference. This one, this is the function inside of the other function. That's the function being cubed. Here though, x cubed is inside the sine function. So x cubed is being, the sine is being taken of x cubed. So you got to recognize which function's on the inside. And let's finish this off with number 4. Tan x is the inside function because it's e to the tan x. So you need to be able to see that, which function is being acted upon. So here, it's the sine x that is acted upon by the cube. So that's the inside function. Here, the x cubed is being acted upon by the sine. That's the inside function. And this last one, I should make a thinner line here because it's kind of hard to see what's going on. That tan x is being acted upon by the e. It's e to the tan x. So tan x is the inside function there. Let's keep going. I don't know why it freezes like that. Okay, here we go. So I'm going to erase this previous problem because it's just in the way. So how do I do this? I have to define the inside function as u. I want to put it to the right because it just fits better when I do it that way. U will be, man, this thing's tripping out. Sorry guys, I don't know what's going on with this thing. Let me quit and restart it. Try this again. So u is the inside one, which is sine x. So if this is u right here, we're going to have y equals u cubed. Again, the thing on the inside right here, that's our u. So it's u cubed. What are we able to find? We can find the change in y compared to the change in u. We can find dy du is 3u squared. And here, it's u and x. Our functions u, our variables x. We can find the change in u with respect to the change in x, and that's going to be cos x, because you learned that in the last lesson, 2 lessons ago. So how do we find dy dx? Well, we need to use the chain rule. What do we have? We have dy du. So why'd we put that first? We want dy on top. There's our dy. We want dx on the bottom. Well, there's a dx on the bottom. So we will have a du dx. And again, that gets us the variables we need, right? Well, dy du is 3u squared. Du dx we found is cos x. We're almost done. Here's a problem. Our variable is supposed to be x, and we have a u there. So we replace u with the original function sine x. So we have 3 sine x squared times cos x. And there's our answer for the derivative of number 2. Let's keep going. It looks like I didn't give myself enough space, so I am going to hide five and 6, and I'll bring it back to life. All right, so number 3, I already showed you the rewritten form. The x cubed is being acted upon by the sine. So the x cubed is the inside function. So I make the inside function u. And I didn't have to be u. I just chose u. It's a very common way they do it in calculus, u substitution. You could pick w, p, q, whatever you want, but u is just a common way of doing it. So we replace the x cubed with u, so we have sine u. And we want the change in y with respect to x. That's our final goal. If you look at this, we can find dy du, because u is our variable. Dy du would be cos u. And here, we can find du dx, and that's 3x squared. And now, if we look, we want dy on top, but we have, on top, we have dy there. But the problem is dy du and not dx. And we realize we want dx on the bottom. Well, there's a dx on the bottom. So we're going to use the du dx. Now we have dy du, that's cos u. Dy du is cos u. Du dx is 3x squared. And we're almost done. The last thing, our variable is supposed to be x, and we have a u. So again, we replace u with x cubed, and that gets our final answer, x cubed times, whoa, that's bad, cos x cubed times 3x squared. Now be careful, you cannot multiply these because this x cubed is stuck inside the cosine function. So this is separate. So to write it a little prettier, we can put the 3x squared first, but remember, that is in the cosine function, it's part of it. If you want, you could put parentheses there, so just to double remind you it's inside, don't mess with it. So that's that example, number 3. Number 4, what will u be? If you see it correctly, u should be the inside function, which is tan x. What does that leave me? Since tan x is u, that's e to the u. I can find dy du, I am my own grandpa, and I can find du dx, which is secant squared x. So we want dy dx. Why dy dx? Because y is our function, x is our variable. So dy dx is what we're trying to find. Now let me do the chain. We want dy on top. Well, there's a dy. So dy du is what I have, so I can use that. I want dx on the bottom. There's a dx on the bottom. So I can do du dx. Well, what's dy du? Well, it's e to the u. And what's du dx? Secant squared x. Now, again, we have the same problem we've had the whole time. Our variable is x, that's a u, so replace that back with tan x. And there is our derivative for number 4. I'm going to do 2 more, but I have to erase some stuff to get it out of here. All right, number 5. Okay, this one, it's a little weird, and you have to recognize how to rewrite this. This is 2x cubed plus 7x to the 1/2 power. So once you rewrite like that, it's pretty obvious that the inside function is that. That's going to be our u. And then we rewrite our function, it's u to the 1/2. Here, I can find dy du, and you should know, hopefully by now, it's 1/2 radical u. And I can find du dx, that's 6x squared plus 7, just using our power rule. And what are we trying to find? Remember, we're trying to find dy dx. Y, the change in y, over x, the change in x. So I want dy dx. The chain will be dy du times du dx. Again, y dy du, I have that available. Y du dx, I have that available. Why in that order? I wanted dy, so there's my dy. I wanted dx, there's my dx. So I have those, and those cancel to get me what I want. Let's go ahead and substitute in. Dy du, it's 1 over 2 radical u. And du dx, that's going to be 6x squared plus 7. And as always, my variable's x, and that's a u. I have to replace that u with its equivalent of x. So I will get this for my final answer. 6x squared plus 7 over 2 radical 2x cubed plus 7x. And again, what did I do? I replaced u with all of that. And that's the answer for number 5. Last one, I'm going to throw you guys off and pick different variables to get you used to using other variables. So I'm going to do cosecant of e to the z. Wow. What function is inside of what function? So you have to realize that e to the z is inside of the cosecant function. So this will be my u. And then what am I left with? W equals cosecant u. Since that is u, I just say cosecant u. Now, I can find dw du because our function's w, our variable's u. I can find how fast w changes as u changes. And you should know this is minus cosecant u cotan u. That you just have to have memorized. And I can find du dz here. That's easy. Easy, because I am my own grandpa. Easy. That's pretty funny, right? Because I planned that. I actually didn't. All right. Let's keep going. We want dw dz. Why that? Just a reminder, I rewrote it that way. So it's the change in w with respect to z is what we want. But where are we going to find a dw? Oh, there's a dw, dw du. So it's dw du, and I want a dz. Hey, I can find a dz here. So that's going to be du dz. Well, dw du I just found, it's minus cosecant u cotangent u. And then what's du dz? That's easy. That's easy. And my last step, I can't have u's. It's with respect to z. So I replace u's with easy. That's easy. Minus cosecant e to the z, cotangent e to the z, times e to the z. And remember, these are inside another function, so I can't combine it with that. But to make life a little prettier, I could put that in front. And I get that as my final answer. That is the derivative of w with respect to z of the original. That is chain rule. We're going to be doing another lesson on this. That's my intro, and you get some practice with your homework. Bye.